Okay, so today let's take a look at this LeetCode problem 215, case largest element in array. So find the case largest element in an unsorted array. Note that it is case largest element in a sorted array, not the case distinct element. Okay, so if we have duplicates, that duplicates your count. So here is the first example. The input array is 3, 2, 1, 5, 6, 4, and then we need to find the second largest element. And it turned out to be 5, right? 6 is the largest and 5 is the second largest. And in the second example, the input is 3, 2, 3, 1, 2, 4, 5, 5, 6. We need to find the fourth largest. So 6 is the largest, and then we have 2 5s, and then the fourth largest number is 4. Alright, so we need to design an algorithm to help us find the case largest element for any given array. And also there's no sense you may assume that k is always valid. A is greater or equal to 1 and less or equal to the array's length. Okay. A brute force idea is we just sort the array in a descending order and then we return the case number, right? Let's give a try. So we need to sort the array in descending order. Okay, and then we need to return the case number. That's gonna be k minus 1. Let's submit it. Okay, so considering we are using array.sort here, this solution gonna be a log-n, right, solution. And what other solutions can we think about? I think another solution we can use a sorted set or hash set to maintain all the variable, all the numbers, and once we exit the case number, we remove the smallest one. Right, but here we need to handle the duplicates. What we can do is, I think we can use a sorted dictionary. Okay, then we just populate the numbers into the dictionary. We need to count the number of elements that we added to the dictionary. So if dictionary already have this value, then we increase the value. Otherwise, we initialize this key value pair. And every time when we add a value, we need to check whether this dictionary has more than k numbers. Okay, if is, we need to remove the smallest one, right? So how can we find the smallest number in the sorted dictionary? So if let's first get the number. Is 1, we just remove it. Otherwise, we decrease the count by 1, right? Okay, so we just populate all the numbers. And what we're gonna do eventually? We need to return the case largest. Right, at this point, we just need to return the smallest value in the sorted dictionary. Okay, let's run the code. Oh, sorted dictionary. Okay, let's submit it. Yeah, it also works. And another solution that we can do is we can use the quick select algorithm. So very similar to the quick sort algorithm. So the idea of quick selection is given an array of numbers. Let's say, let's just use the first example. So our input is 3, 2, 1, 5, 6, and 4. So say we need to return the case largest. So we need to find a pivot that such that all the values, all the numbers on its left side is smaller or equal to this pivot. Or the elements that are on the right side will be strictly larger than this number. Right, every time we find a pivot and we partition this array into two parts. Right. Let's say if this is our pivot and our target index gonna be so this is n-1, our last index. And if we want to find the case largest, the index will be n-k. Right? Say we want to find the third largest. This is going to be n-3 because we have n-2 and then n-1. And we use this number to compare with the pivot location, pivot index. And then we determine whether we go to the left side to continue the partition or we go to the right side to do the partition. That's kind of the idea. Okay, let's implement it. Let's clear this one. So let's first find the define the left and the right. And also the expected index is lumps.length minus k, right? Then we just do the partitioning until there's only one element and left smaller or equal to right, and we do partition. So partition, we gonna give the numbers array and then left and right. Right. If pivot location is the expected index, we just return number at the expected index. Otherwise, if pivot location is smaller than expected index, what we do? So our expect index is here. It basically means we need to keep partitioning on the right side. Right, otherwise we go to the left side to do the partition. Okay, by default we just return a minimal integer value to indicate there's not such an answer. Okay, now let's implement the partition function. We're gonna give the numbers array, the left and the right. Okay, so the idea, let's just use this example again. So every time we kind of find a base, in this case we use the rightmost one. This we call it pivot. And also we define a pivot location. Initially we set it to 0. Let's call it pivot location. And then we use a pointer to help us iterate this array. So every time we compare our current value with our pivot value, if the current value is smaller or equal to the pivot value, we switch the number at our pivot location and I. And then we move our pivot rightward by 1. So in this example, 3 is smaller than 4. Okay, we swap the number at index P and index I, since they are pointing at the same value, so it switched by with itself, right? And now we move the pivot index. And next iteration, we move I rightward by 1. We compare 2 and 4. Okay, 2 is smaller than 4. We do the same operation with first swap and then we move the pointer p rightward by 1, and in our next iteration we move I rightward by 1. Okay, 1 similarly we do the swap first, then we move the p rightward by 1 and move the I rightward by 1. Okay, now 5 is greater than 4, so in this case we don't move the pointer pivot location. We don't move the p here. So in the next iteration, okay, 5 or 6 is also greater than 4. Okay, and we don't do the swap. And we don't need to compare the last value with itself. So when I is less than right is the condition we do the operations. If I equals to the right, we stop. And after all these operations are done, what we do is we swap the value at at index right and the pivot. So in this case, we swap 5 and 4. So what we can see here, after the swap operation, all the values on the left side is smaller or equal to 4, and all the elements on the right side is greater than 4. Right, that's kind of the idea. Okay, let's implement it. And the pivot location, initially we set it to left. Okay, if numbers at I is smaller than or equal to our pivot, we do the swap. We swap our I and our pivot location. And also we need to increase the pivot location by 1. Okay, after all this operation, we swap the pivot location and our right. Numbers, pivot location, and the number at the right index. Eventually we return our pivot location. Okay, last thing, we need to implement the swap function. Oops, this is temp. Okay, so let's compile the code. Yeah, I need to return. Okay, so what's going on? Let's quickly review. This is our initial left and right point, and this is our expected index. And we start the pivot, partition, and if our pivot location is the expected index, we just return the value at the expected index. If our pivot location is smaller right, is smaller, then we go to its right side. Oh, if our pivot location is smaller, we go to its right side. Okay. Okay, let's submit it. Okay, so what's the complexity of this solution, quick selection? So the worst case is every time we only eliminate one number, right? Let's say we only eliminate one number. So the first time we need to iterate n numbers, and second time is n minus 1, and eventually we have one element. So this is arithmetic sequence, so it's 2 n plus 1, so this is the sum. So this worst case is n square time complexity solution, but on average every time we just eliminate half of the value, right? Eliminate half of the value. Ooh, crash. 1 second. Okay, it seems like the app is crashing now, but if every time we eliminate half of the number, that will be first time we handle an element, the second time we handle half of the element, right? And then oops, and then third time we divide by 2 again, so it's gonna be like this. Eventually we handle only one number, so this gonna be a ON. Averagely it will be a big ON time complexity solution. Still crashing. Yeah, well, it is what it is. That's it.